Hello everyone, welcome back. In this video we're going to talk about the inverse cosine and the inverse tangent function, which will finish out section 8.1. Now, I made this video right after I finished the disaster of the last video, and the approach that I was trying to talk about then was called the reference angle approach. So I found a reference angle, and the trig function of a reference angle is the same up to a sine of the original angle. Okay, so that's what I was trying to talk about before. It probably made no sense now. Then it hopefully will make some sense now. All right, so back to what we're going to talk about in this video, the inverse cosine and the inverse tangent function. So the inverse cosine function is going to follow the same general pattern as the inverse sine function did, okay? But it has slightly different shape. And so you'll remember that the inverse sine function, in order to get an inverse, we had to restrict the domain of the regular sine function to between negative pi over 2 and pi over 2. That doesn't work for cosine because it's not 1-to-1 from negative pi over 2 to pi over 2. So we have to switch our domain to 0 to pi. Okay, so that's the blue section of the cosine function down here. So it's going to act very similarly to what we did in the sine function part, but now our range is 0 to pi instead of negative pi over 2 to pi over 2. And so what that means for us is that we're going to be working in the first and in the second quadrant, not the first and the fourth quadrant. Okay, and so again, inverse cosine means that you switch x and y and you solve for y in the original cosine function, okay? And the domain of the inverse was the range of the original, which is negative 1-to-1, and then the range of the inverse was the domain that we had to restrict the original to, 0 to pi. All right, and so let's try again finding the exact value of an inverse cosine function. And so I have on the right a nice table that's going to help us solve this function, but I'm not actually going to use the table because I'll assume that you won't have the table during other times, but I know you will. That's a side note. Anyway, cosine inverse of negative square root of 2 over 2. All right, again, I don't like to work with inverse functions, and so I'm going to try to find a way to get myself to a regular cosine function. And lo and behold, if I take the cosine of both sides, okay, I set it equal to theta, as usual, and then I take the cosine of both sides, and that gets me down to the cosine of theta equals negative root 2 over 2. So again, I play the game of I have an angle that has to be in the first or in the second quadrant. Okay, so I've narrowed it down to the first or the second. And I have to think, where is cosine negative? Everything is positive in the first quadrant. Cosine is negative in the second quadrant. Okay, so I've got a negative, cosine negative in the second quadrant. That means that my angle must be in the second quadrant. So I draw my triangle over there, and I have to think, what special triangle am I going to use? The 30, 60, 90 triangle has 1 square root of 3 and 2, and it doesn't look like I could get the square root of 2 over 2 from that. But in fact, it does look like I can get square root of 2 over 2 from the 45, 45, 90 triangle. Okay? And so square root of 2 over 2 comes from, that's really the same as 1 over the square root of 2, which will make some sense. Okay, so I draw the triangle in the second quadrant, and I draw my legs of 1 and then negative 1. Okay, the opposite leg is going to be 1. The adjacent leg to the angle is negative 1. And then the hypotenuse is square root of 2. And then I have to think, what angle does that represent? That represents pi over 4, okay, which is my reference angle to the original angle that I want, which is 3 pi over 4. Okay, so that gets us to the answer that the exact value of cosine inverse of negative root 2 over 2 is 3 pi over 4. Okay, so that's the same sort of steps as we did in the inverse sine function. Hopefully it's making some more sense. Probably was a little confusing then. Hopefully is a little less confusing now. All right. Then, again, I could work with cosine inverse and cosine together, just the same way as I did before. All right. And again, it works very similarly to sine, but now f inverse of f is equal to whatever's inside f if that whatever's inside that x is between 0 and pi. It used to be it had to be between negative pi over 2 and pi over 2 for sine, but now, of course, it's a little different for cosine, 0 to pi. And then the other way works the exact same as it did the last time. With sine, the cosine of cosine inverse of x is equal to x when x is between negative 1 and 1. All right. So here I have the easy example, cosine inverse of cosine of pi over 12. Pi over 12 is between 0 and pi, so great, it's equal to pi over 12. Okay? That's what you hope and pray for on every exam as a student. And then, of course, there's the not-so-nice example, cosine inverse of cosine of negative 2 pi over 3. Clearly, negative 2 pi over 3 is not in the interval 0 to pi, and so I can't use that first fact up in the yellow box. So I have to, again, improvise, set whatever is the inverse, which happens to be the outside, everything, equal to theta, and then solve. Get rid of the inverse, and then I have something I can work with. So I get rid of the inverse, and I get cosine of theta is equal to cosine of negative 2 pi over 3. Now, that may be a little hard to work with still. Okay, you may not have a good idea of what's going on, but cosine has a nice property that cosine is even. Okay, sine is odd. Sine and tangent are odd, but cosine is even. And even functions have the property where f of x is equal to f of negative x. Okay, so the positive and negative values of the inside thing, when I take the function of those values, they are the same. So hopefully that explanation made some sense. Because of that fact, I know that the cosine of positive 2 pi over 3 is the same as the cosine of negative 2 pi over 3, because cosine is even. So I'm thinking 2 pi over 3, does that make sense? Is it between 0 and pi? Yes, and so that's the answer. Okay, so that's inverse cosine. And then lastly, we go to inverse tangent. Now the tangent function, unlike sine and cosine, is 1-to-1. So it passes the horizontal line test between, so this function, when you repeat it for a bunch of times, no, it doesn't, of course, but if you take in between the vertical asymptotes, it is a 1-to-1 function. So, of course, we're going to look at the middle of vertical asymptotes of negative pi over 2 and pi over 2. That's the inverse tangent, or that's the tangent function that we're going to work with to get the inverse tangent. So, that's the one we're going to look at. And so, when you make the switch, again, the regular function is in red, the other function is in blue. Okay. Inverse tangent, you switch x and y, solve for y, great. The domain of the inverse function is negative infinity to infinity, because the range of tangent, usually the original function, is negative infinity to infinity. And then, of course, we restrict our view of the domain to be between negative pi over 2 and pi over 2. And the thing that has changed between sine and cosine and tangent are that you'll look at the inequalities here, they don't have or equals to, okay? And that's, of course, there because the vertical asymptotes are at those points, okay? So now y has to be between negative pi over 2 and pi over 2, and it can't be those endpoints. So it's a slight difference that only is going to make a difference 1 in a million times. But it's important to recognize. So again, I go through 2 examples with the inverse tangent function, they follow the exact same form as sine and cosine. So I'm not going to talk through each of them, but they are here to look at, and I'll answer any questions that you have through email or Zoom or whatever. Okay. And so the inverse tangent function, again, works the same as sine and cosine, so I didn't put any examples here. But what I do want to talk about is finding that inverse. So we sort of know the calculator has these values for just like regular sine inverse, but what if I have something more fancy? Can I do it on my own? Or can I do something different than just sine and sine inverse? And the answer is yes. Okay, so I have a regular function here, y is equal to 2 times the sine of x minus 1. Okay, and of course you'll notice that it's defined between negative pi over 2 and pi over 2 inclusive, so that I can find an inverse. Okay, so you find the inverse by switching x and y and solving for y. So that's exactly what I do. So x equals 2 sine y minus 1. I add 1, divide by 2, and then take the inverse to get the inverse function, which is y equals sine inverse of x plus 1 over 2, where y is between negative pi over 2 and pi over 2. Okay, so that's the inverse function right there, and then I ask you to find the domain and the range. So the range is right there. Y is between negative pi over 2 and pi over 2, but the domain is a little different. So the domain usually is whatever's on the inside has to be between negative 1 and 1. Okay, and so usually it's just an x, and so you say x is between negative 1 and 1. But now I have a formula in there that I need to solve for x. Okay, so now I have that negative 1 is between, that x plus 1 over 2 is in between negative 1 and 1. And so when I multiply both endpoints by 2 and then subtract 1 from both endpoints by 2, I get that x is between negative 3 and 1. Okay, so hopefully that little algebra that I did there made some sense. And so I get my domain and my range for my inverse function. All right. And now the last slide that I want to talk about is solving equations involving inverse trigonometry functions. So you may see this, or you definitely will see this sometime on an exam, a quiz, the homework, solving equations involving inverse functions, specifically inverse trig functions. So I've got the equation 3 sine inverse of x is equal to pi. All that I want you to do is solve for x. Okay, solve for x. So I divide by 3. Great. Okay, then I take the sine of both sides, which gets the x alone, and I get the sine of pi over 3. Okay, and the sine of pi over 3 should be easy to find. Okay, that's stuff that we've been doing for a little while now. I draw my 30, 60, 90 triangle because pi over 3 is 60. Okay, draw the 30, 60, 90 triangle, and I get the square root of 3 is the opposite side, 1 is adjacent, 2 is hypotenuse, and the answer is square root of 3 over 2. Okay, so that's it for this video and the end of section 8.1. Hopefully that made some sense. We're going to move on to section 8.2 in the next video, which are just the inverse functions of secant, cosecant, and cotangent. I'll see you next time.